Modern science relies on the assumption that solid objects occupy a pre-existing container of geometric space and time. The Relational Admissibility Framework, or RAF, suggests that space and time are secondary outcomes rather than fundamental foundations. Space and time appear as rendered maps, byproducts that emerge from stable relational networks. By calculating the network itself, we can determine the behavior of any system, from a quantum wave to a biological tumor, using 4 mathematical operators. This approach identifies a shared mechanism between quantum probability and tissue disease. Both are driven by a specific topological breakdown in how a system connects to itself. These 4 operators, relation, closure, persistence, and propagation, form a mathematical toolkit for calculating systemic stability. We will build these operators from the level of pure distinction and use them to identify the exact moments when macroscopic systems fail. Computing the universe depends on calculating how things relate rather than measuring their physical coordinates. We begin with pure, undivided reality making its first mathematical distinctions. This brings us to the relation operator. Before anything physical can manifest, 2 isolated points must establish a connection. The first variable of relation is accessibility, or ρ. This measures the strength of the bond between the 2 points. The second variable is phase, or phi. This represents the mathematical ordering or the specific spin of that connection. Isolated relationships remain unstable until they link with others to form complete loops. The closure operator describes the moment these phases synchronize within a loop, locking the pattern into a stable state. When phases in a loop conflict, they create frustration. This mathematical mismatch prevents the pattern from settling. This provides our first universal rule. Stable existence at any scale requires low frustration closure. To understand how a mathematical loop becomes a physical object, we must look at how it maintains its shape. The persistence operator measures this survival. A pattern becomes a distinct thing when its internal coherence exceeds its external leakage. Persistence creates a boundary of inside versus outside. This threshold defines the limits of atoms, cells, and macro objects. Physical objects represent self-maintaining closure patterns that have successfully achieved persistence. As trillions of these persistent knots interact, they form a vast interconnected network. This web reveals that our perception of geometric distance is actually an interpretation of network health. We perceive distance when relational accessibility drops. The harder it is for information to cross between 2 points, the more space we see between them. In this framework, distance is the negative logarithm of that connection strength. The propagation operator then dictates how disturbances move across this network of connections. Space is a map of stable adjacencies, meaning physical proximity is an outcome of network accessibility, not a cause of it. In complex biological tissue, these exact same relational rules govern how cells dynamically divide and organize into larger structures. We can model tissue as a multi-scale architecture of closure relationships, where every cell must coordinate with the whole. Morphogenesis is the process of the tissue network finding its most stable, low-frustration geometric form. By applying these operators to health, we can redefine disease as a failure of this coordination. Normally, cells balance their internal functions with signals from their neighbors. Cancer represents a break in equilibrium. A local cluster of cells hyper-synchronizes internally, effectively locking the rest of the tissue out. The result is a persistent knot that grows independently of the organism's overall pattern. This rise in relational frustration serves as an early warning, appearing before any visible structural changes occur in the cells. Biological disease begins as a relational conflict, which makes it mathematically detectable before the body physically breaks. This framework offers a method for moving from theoretical physics to actionable clinical science. One primary prediction is distance-independent influence, where relational closure overrides physical geography. Tissues on opposite sides of a body may influence each other more strongly than their immediate neighbors if their relational phase alignment is higher. This biological non-locality mirrors the physics of quantum entanglement, showing that both are results of the same topological connectivity. This leads to coherence-first medicine, which analyzes pattern stability instead of isolated chemical markers. This health score equation tracks systemic risk by comparing phase coherence, or psi, against the system's frustration. Successful biological regeneration depends on restoring the overarching topological pattern. Localized chemical or cellular replacements function as temporary fixes for a deeper structural failure. These rules apply to ecosystems and human brains alike, where health is defined by the stability of the entire network. Cognitive intelligence reflects the ability to maintain high network coherence while remaining flexible enough to reconfigure when the environment changes. Reality consists of emergent patterns striving for relational stability. To repair any system, from a quantum state to a human body, we must identify the exact pattern that has failed to close.